Hi, so I'm John Pacific, otherwise known as Tux at NuCypher. At NuCypher, we're building the data privacy layer of Ethereum, or any blockchain for that matter, really. So just to go over what we are, who we are, what we do. We're building tools developers need to make build privacy into their applications, specifically for decentralized or distributed applications. Our core tech that we use for our network is something called Proxy Decryption. I'll dive into what that is. But some other things we have going on are based on lattice-based cryptography, like fully homomorphic encryption. And we also do some research and development on the side for that. Our team is composed of cryptographers, software engineers, distributed systems developers, security engineers, people with a variety of backgrounds work for us. So with that said, what we do at a core is decentralized access control through threshold proxy re-encryption. So we'll take this down step by step of what we currently have and what the problem is and what NuCypher allows us to do. So we'll ask like a very basic question. What are the limitations of traditional asymmetric crypto, right? So let's take the traditional file sharing narrative that we currently have with just regular public key encryption. So on Alice's side, if she wants to grant access to some data with her using somebody else's public key, first she'll encrypt that file using the other person's public key, of which they will then receive that file, decrypt it, and then have access to it. But this is problematic for a variety of reasons with regards to access control, because once you've then encrypted it, that person can always have access to that data wherever it's stored. So in this case, on Alice's side here, Alice will encrypt something and then say something can be decrypted using just traditional symmetric key cryptography, and then re-encrypted using just another traditional scheme again through a middleman here in like that little box, Alice's client side right here. So essentially, to grant access to Bob, to Charlie, so on, it has to be encrypted each and every time with their own public keys. For one, this doesn't really scale that well unless you're building like some huge public key infrastructure, which unfortunately doesn't really exist in our current scheme of things for the decentralized internet, nor is it really probably the best idea to do it, because we saw how certificate authorities panned out for the current internet, and things like that aren't going the greatest, and so now we're trying to hack around and build things to sort of inspire trust there, and they're not really working that well. There's a few solutions, but clearly for Web 3.0, we need a new solution to build a privacy layer. So in this case, what you're seeing is a proxy. That little box is essentially Alice is encrypting some data with her public key. And then on the client side there, it'll be decrypted and then re-encrypted for the recipients again. And then that way, the person has to go through that proxy to gain access to that data. So if you're on the remote server, like it says here, anybody who has access to this can then see the data. So what happens is, if your remote server is being run by, say, Vladimir Putin in Russia, or just some hacker has compromised it, they'll be able to see the data as it exists, as it transitions from one encrypted state to another. And that's bad. So even similarly with decentralized storage, there really is no way to achieve this in a decentralized, trustless manner. And that's what we solve with threshold proxy re-encryption. So in this case, if you put something on the blockchain, everybody else can see it. So now you've put some plain text data on the blockchain. Maybe you don't want somebody else to see that plain text data, right? Maybe you don't want to store some ciphertext on there forever with some granting out keys as much as you want. So we say that proxy re-encryption closes this loop. Essentially, what you see here is that proxy re-encryption is a method where normally we have Alice will encrypt something with Bob's public key. Instead, Alice can encrypt something with her own public key and then generate a re-encryption key for the recipient. And then pass along that re-encryption key to what we call a proxy. And then that proxy then performs the re-encryption, and that then allows Bob or Charlie or whoever to gain access to that data. These re-encryption keys, there's different schemes for this. Currently, we use something called Umbrel, which I'll go into more, which is the threshold variant. But there are some earlier research. So there is prior research and prior literature on the exact schemes that we use. But yeah, it's very simple. What actually happens here is that when ciphertext is encrypted under Alice's public key and then it's gone through a transformation from a re-encryption key, it actually transforms the ciphertext from Alice's key to Bob's key, or whoever the recipient is, in a very, what we call an atomic manner, meaning that it just transitions right then without doing any further operations. Yeah?
So Alice will send this data to the proxy, and then when the proxy sends it to Bob, it decrypts it with Alice's key or somehow, and then it re-encrypts with Bob.
So it actually never decrypts the data. That's why proxy re-encryption is very interesting. It actually never decrypts the data in that state transition. So if I go back to this slide here, you'll see where we have that state transition where it decrypts the data, and then it re-encrypts it again with under another recipient's public key, right? So we don't actually have to do that anymore with proxy re-encryption. What's happening here is that the ciphertext is literally getting transformed from Alice's key to Bob's key. The proxy, at no point in time, actually sees the plain text. Yeah, it's pretty cool. So we have a few characters on our network, and more will probably come, but we'll just go over what these are. And some of these you're already familiar with, Alice and Bob. For example, we'll just say these. Alice, in our network, is a policy owner. We like to say that Alice is like the authority of some sort. She is the one who grants access to other people. Anytime a person wants to gain access to Alice's data, they become Bob, the data recipient. Right? So Alice will be granting access to a number of Bobs throughout the policy lifetime. Ursula is the staking node on our network. Ursula is this proxy node. People will stake our token, and I'll get more into what the token is for. But the proxy node is the one who's literally doing this transformation function. So if I go back here, Ursula is this proxy person in the middle. We call her Ursula because it stands for untrusted, U for untrusted, because we don't trust them on our network at all. So what happens is she's actually calling this re-encrypt function that you see here using a re-encryption key and then a ciphertext to re-encrypt for another person. Enrico, what we realized early on while building this was that Alice, normally, if you see something, the data owner isn't necessarily also the source as well. Somebody can own data, but have data come from another device. For example, I am me, okay, and say I have several devices. I'm Alice, but my devices may be Enrico, this data source. We call him Enrico for E, which is the encryptor. So Enrico is actually going to be encrypting stuff for the policy, and that data will then get transformed for other people. So with that said, go back over this again. Traditional data sharing with public key encryption. A single node has access to data, and a single node can deny access. So this is like what you may think of with traditional PKI, public key infrastructure. A sender will encrypt some data under one key, and that single node can have access to data. It can be colluded with. You can pay them off to give you access to data or whatever, but the receiver goes to that node and says, can I have access to this data? And that relies on that one node's permission to give you that data, which is also problematic in a trustless setting, because since we're building decentralized and distributed applications, we require that our applications are trustless. With proxy re-encryption, instead, the sender is given a re-encryption key, the proxy, that single node, is given a re-encryption key. Single node collusion in this setting, where it's not threshold, where they just have the single re-encryption key by itself, collusion is possible with the receiver. What that means is that the receiver can essentially pay off the proxy node, in that case, to say, forget about Alice, just always give me access to this data. Now that may work in other traditional settings, like say corporate environments in some cases, but depending on the threat model in that corporate environment, that may also not work either. Problematically as well, a single node can also deny access. So for some reason, say you're running a node in China, right? And You're a company that's running some nodes in China, and you've been told that you can't give access to Chinese citizens. Okay, well there's a problem for Chinese citizens there. How else are they supposed to gain access to this data if they have to go through that one person? This is where threshold proxy re-encryption comes in. Collusion to perform any of these attacks would then require M nodes and the receiver to collude together to prevent access. In traditional proxy re-encryption schemes, the receiver can collude with the proxies or the Ursulas to gain access to Alice's private key or just gain access to the data. But in this case, that kind of thing would require collusion with all these nodes together, plus the receiver himself. So to quickly go over this, the NuCypher token is used to coordinate our network. You stake our token, that way you can start earning rewards on our network to incentivize you to keep going and maintaining the health of the network. We allocate re-encryption keys proportional to the stake that you stake. And we also compensate honest nodes and / malicious nodes. So it's used as a game theoretical, like economic behavioral control. So for example, if you perform a incorrect re-encryption, let's say you provide just bogus data instead of providing an actual re-encrypted piece of ciphertext, then we can actually use we use zero knowledge proofs for this. They're very simple. And if you provide an incorrect one, we can prove it on chain and then slash that node for doing that, which effectively can get them kicked off the network and they can't perform re-encryptions for us anymore. So that kind of thing allows us to actually repair the network if there's any sort of malicious activity going on there.
When you slash them, they lose new tokens, is that it?
Yep, so to join the network, you stake the tokens, and if you perform an incorrect re-encryption, you'll lose those tokens. Yep. Oh, great.
And who decides that?
Sorry?
Who decides whether or not to slash malicious nodes, or whether that even constitutes malicious?
Sure. So the question is, just so I can restate it for everybody, is who decides when an incorrect re-encryption has been done, right? And how can we decide that an incorrect re-encryption has been done? So like I said earlier, we use zero knowledge proofs to know when a re-encryption is done correctly. That way you can prove to the receiver that and say, hey, I did this re-encryption correctly. Here's a proof for it that the output of my re-encryption function is the correct output of this re-encryption function, given some input or some private input. With that, we can then use that on chain. So now with that public information, we can actually prove that on chain. So those proofs, if for some reason, we don't need to verify every proof. We only need to verify proofs that are bad. So if you give a faulty proof, then you can upload that on chain and so that's just the Ethereum blockchain for us. So when it goes through a smart contract that performs the proof, and if the proof is invalid, it will slash it. Does that answer your question?
Yeah, I understand, but I was wondering maybe there's some edge cases where you cannot prove 100% that they are bad actors.
So the proofs we use are just very generic. They're not like zero knowledge. They're not like ZK snarks or anything. It's just a Sigma protocol, which if you're familiar with that, it's a really, really simple proof. But there are no really edge cases. It's just you're proving that you have knowledge of something and that you did a certain function, that the output is the correct one. So there aren't really any edge cases to be concerned of there. I will stop here for just a bit. Are there any questions on our network? On our network at all, if I haven't touched on anything?
So, talking about certs and state level actors, with X509, couldn't I, as a state level actor, surround and partition the person I'm trying to attack, think that they're going to M nodes, but the M nodes I control? Can I, as a sender, determine which nodes I try to reach to do work?
Yes. So what you can do is we go to the blockchain and we say, I want a policy that has where I give out 5 threshold re-encryption keys to it, right? And the blockchain will be like, okay, according to stake, here's the nodes you can use. And then if you don't like those, you can go again and be like, I don't like those, give me another one. And so it'll give you more. So you can keep going until you have a proportional amount to do that. So it's really difficult for a state level actor, unless they were to stake a good portion of tokens and become a majority party in the network. then it would be quite difficult for them. And even still, even if they did collude and gain all access, the most they could probably do is deny access to data, which of course, if you're Alice, if you're the recipient and somebody comes to you and says, hey, I don't have access to data because of some network level adversary, I can just re-grant the policy again. So it's kind of difficult for a state level actor to actually get around and try to break into.
So what about attacks where someone just uploads some data, but the nodes or the proxies, they just completely garble the data to make it all?
So that's what I was talking about with the correct re-encryptions. The question is, what if the node just gives garbled data instead of the correct re-encryption? In our case, if they do that, then they'll also have to provide a proof with it. If the proof can't be validated, they'll just get kicked off the network. Because we can provide the invalid proof to the blockchain will kick the person off.
Okay, so you talk to the Ethereum blockchain.
Yeah, that's where the slashing mechanics come in that I was talking about, where essentially you stake to join the network, and you'll get re-encryption keys to perform the re-encryption. And if you provide an incorrect proof, the proof can be validated and prove that it's incorrect.
So the chance, you guys don't really have a blockchain, you just have some client software, and then that talks to the blockchain.
We're a layer 2 application. We're based on Ethereum right now. Ostensibly, we could probably move to any blockchain that allows us to perform some smart contract validation. Yeah, we don't have our own blockchain. We're just a layer 2 app. Cool. Everybody, we're clear? Moving on? Fantastic. So we do have a private test node. This is where it's going to get a little cool. If you guys want to try out what I'm talking about, I'll go over through a demo of what you can do today. But please read our docs.NuCypher.com. We have different domains for our testnet, so we know who's using what. That way it's easy for us to track development, see what's going on. We call this Oumuamua after the space object that was recently identified. Don't ask me how we decided on it. I don't know. It's just a good name. So we also have a seed node. So the way our networking works is you have to know a node in the network that knows all the other nodes, or some of the nodes, and then you can go to those nodes and talk to those nodes and see and find out about more nodes. So right now, I host a seed node on my domain, isogeny.tux.sh. And this is what I will be demoing and using. So, but feel free to use this node as well. I provide it as just a DNS name resolver, so no big deal. Feel free to use it for your own applications, not in production though, just for testing. So before I get into that demo, normally I would do a demo there, but I'm going to do the demo at the very end. Just to go over some other things we're working on. We're also working on fully homomorphic encryption. If you're not aware of what fully homomorphic encryption is, it's the ability to compute unencrypted data. So, for example, just to go over this, say you have some data, say it's like an integer. So we'll say the number 2. And say you want to add 2 and 2 together. So you have 2 plain text integers, 2 and 2. The output is 4 when you add them. If you were to say, let's say this function that we're talking about here is an addition operation. Obviously, we can add 2 and 2 in the plain text, and we hopefully get 4 if physics and math hold strong. Otherwise, in the encrypted domain, so the idea is we can encrypt that data and still add the ciphertext of 2 and the ciphertext of 2, and add those together and get the encrypted ciphertext of the output of that function. In this case, it would be an encryption of 4, but you wouldn't know that. You would only have just an understanding of what the ciphertext is. Now, fully homomorphic encryption doesn't just apply to addition, obviously. It also applies to multiplication as well as logic gates. So in our case, we have built a library called NuFHE, which is an implementation of TFHE, if you're familiar with any of those libraries. What it is a GPU implementation of fully homomorphic encryption, TFHE, and it has achieved, I could be wrong, but I'm fairly certain I've done a lot of digging on this. I think we have the fastest FHE library ever right now, and only because we do it on the GPU, and also because we do some really cool fast Fourier transform and NTT stuff, number theoretical transform to make it really fast. We use it to execute the first ever fully homomorphic smart contract at ETH Berlin. First ever. That was, thanks. Yeah. It's something I wrote in maybe like 30 hours or so called Sputnik. What it was is simply just a kind of like an assembly language, like bytecode-ish language that will allow you to build a VM and run operations based off of just like some operations you specify.
Did this work on like the Ethereum mainnet? Like you could just deploy a contract with?
So it wasn't. So it was smart contract. I think is used very loosely here. I think I use it just by the terms of like what I did was actually use just a method of proving that a computation was done on a piece of data. So I would commit a Merkle root of this computation. And when I say that, and I'm diving into really specifics here, but
So you get all the opcodes, you line them up, and then get the Merkle root of all the opcodes.
yeah, exactly. So you perform an operation, and then the output of that operation gets hashed, and then you get another operation as it just goes down the VM, down the stack, and then it organizes it into a Merkle tree, and then you commit the Merkle hash of that, the root hash for that, and then you can pretty much pick out spots of that and say, oh, I need to prove that this piece of data I've received was used in this computation, which you can do using a Merkle proof. Yeah, so that's what you would do, and that way you could be performed locally. It wasn't a huge like smart contract like you'd normally think of, but it is like that's why we called it Sputnik. It's like launching the first ever satellite, just to kind of plant the flag in the ground and say, we're doing this. So yeah, it's really cool. It's achieved some pretty considerable speed ups over normal other libraries that are out there right now. And I also have to touch on this, and I can't stress enough how cool this is. CoinList and us have partnered together to do a virtual hackathon. It's going from March 11th to April 7th. We have $25,000 in prizes to hand out to winners. You can get a lot of details on this by going to coinlist.co, build NuCypher. And we have, if you join our Discord, if you're building on this, we will provide as much support as possible. It's been like super critical for us to help the community build on our stuff, as well as helping you guys debug your applications and help us figure out where we might have made some mistakes. So it helps us a lot if you guys build on this, and we're really excited to see what people build for it. So you can see our website, NuCypher.com, documentation. Some more information, NuCypher.dev goes to our GitHub repo, so you can see everything there. We have our Discord. Please join it. You can email me if you have any questions after this presentation at john@NuCypher.com. And then also our Twitter account at NuCypher. Just to go over some quick use cases here. This is our current public list of users. Bluezell, Fluence, and Volk are all using us since they are decentralized databases, they use us for access control, which we think is really, really cool. Medical data protocol, also really cool. So in this case, if you're a doctor, or if you're a patient of a certain doctor, you can grant access to that doctor to your medical data and then revoke access later on. That way, you don't have to trust that the doctor is going to keep it. And yeah, so I guess for this point, it's time to jump into the demo, if there are no more questions.
The examples, are they all in production?
All these NuCypher in production?
Yes.
Not quite yet. They are working with us to run on our testnet.
Who's the closest you would think of all projects?
Let me see. I think probably Mediblock, maybe Carblock, and maybe Fluence and Bluezell. I think those are probably our closer ones. We work pretty closely with those guys.
So how do you feel building on top of Ethereum with all the criticism?
In all honesty, building on Ethereum is really rough. The reason why is because it's super early. This is a super early space, right? We're all still trying to figure out how this thing even works right now. And like stuff like that I had a problem with, like we just now, like we put up some bounties to get people to start hacking on stuff so we can actually solve some major problems. But like signatures on Ethereum were horrible and are still kind of horrible for like Geth and parity. But just recently we just had chains merged into those things to actually use it. Since we're in the Python ecosystem, we've seen like a huge lack in Python tooling. So a large portion of our time is actually spent maintaining some Python code bases that people don't want to maintain anymore. Everybody seems to use JavaScript, which isn't great when you're working on a cryptography like heavy application, because JavaScript is just in time. So it's not, you can't verify that it's constant time at all. But yeah, it's kind of weird building on it. I wouldn't change anything about it. I like building in the space. The problems are really, really cool. But yeah. Any other questions before we get into this demo? No? All right, let me switch laptops here. Great. All right. So what I'm going to show off now is our actual endpoints. What you will do as a developer is you'll build on what I'm going to show you. Normally, if you're running a Python application, you don't have to do some of the stuff that we've built that I'm showing off. But most people we found want to use maybe JavaScript or some other language, and maybe not just necessarily Python. So we built a way of doing that using just kind of the old, if you remember how when you use Bitcoin D, you'd spin up a daemon and you communicate to that daemon. That's what we've written for all of our characters on our network. So if you remember back in the beginning of the presentation when I went over some of the characters and what they do, you'll see me spin those up. Now Ursula is already running on our testnet. That's that isogeny.tux.sh, if you remember. That's just a seed node to learn about the entire network. So let me open up IPython here. And I'm going to go just to import some stuff that I'm going to use throughout the demo. So I'm going to be using some JSON, some requests if you've used that Python library before, and also just basic 64 encode, decode. All right, now to get into it, we're going to start spinning up Alice. If you remember Alice, she's our data authority. She's the data owner. She's going to be granting access to this data. So I have this commented out, by the way, if you'd like to see it later on. But I'm going to run Alice in this little top right corner here. So I'm actually going to type NuCypher Alice run, put it in dev mode, and federated only. What federated only is, for our test node, for our testnet is, we've spun up a federated testnet. This is probably what you're familiar with, just regular peer-to-peer applications, like back in the days of Kazaa, LimeWire, even the Tor network as it runs today. We didn't want to include the economics components yet to test all the characters and how they work. We have some PRs that need to be merged, and once we do that, then we'll just be on Decentralized testnet where we can actually practice staking and working with that stuff, but we're taking it one step at a time. So for right now, we're not concerned with the economics part of this. And as a developer, you don't need to be worried about the staking parts of this either. So I'm going to pass in something called a teacher URI. What the teacher URI is the node that's going to be teaching that character that's running about the network. They're going to hear back and say, here's other nodes on the network that you can also talk to. So I'm going to spin that up. So it's fetching it. OK. It just learned about all the seed nodes on our network, probably because I already ran it. But we have something called a learning loop that goes through and learns everything. So now I'm going to grab this verifying key if it doesn't run away from me. But this verifying key here, and I'll go over everything in this terminal before I skip through it. But right here, so what we're going to be doing is we're going to be talking to this daemon, localhost on port 11, or sorry, localhost on port 8151. That's actually our Alice. You see me name it Alice. And we're going to be making a request on an endpoint on that daemon using just traditional REST, which is derive policy pub key. So what we're going to be doing is deriving a public key for a policy that now Enrico, the encryptor, can then actually actually encrypt data for and gain access to that, and then Bob can later gain access to that data. So I've just made some little points there that I'm going to use later. Policy encrypting pub key, Alice verifying key. These are things we would normally store and that you transmit with in your application, but I have to show that this way. So I made that request. So you can just see it's just REST like that. Let me pull out that. There we go. Just need the policy encrypting pub key. This is actually what Enrico This is the public key that Enrico, our encryptor, is going to encrypt for. So Enrico doesn't have access to that data, to that private key. Only Alice does. And ostensibly, Alice doesn't really know, cannot, from just a given ciphertext without a label, what we call a label, can't really derive what that private key might be. So if you see this label here, I've named it SFCDEVS. What a label does, it allows you to pretty much designate what that data is for. So when you encrypt some data, you want to be able to say, oh, this is John's data, or so on, right? Typically, what we would recommend is that you use a label per recipient. That way you can maintain, and also per policy, that way you can maintain some semblance of forward security or secrecy with that. It really helps. It really significantly increases the security of your application in comparison to just traditional public key cryptography. So, yep.
Talking to
Alice. It's the top right here, or the top right. We call this demo the Brady Bunch demo because it's like just a bunch of terminals all over the place. But if anybody's confused at any time, let me know. I'll let you know.
You're gathering all these nodes, and these nodes are people that you trust to send encrypted data to, and that you can talk to as Bob and get Alice's data, and then they'll perform.
They won't get Alice's data, right? So
Alice will send it.
Alice. So the thing about the NuCypher network is we don't handle the transport of your bulk data, as we call it, right? So if you're encrypting a movie, we don't worry about where you put your movie. You can put that on IPFS, you can put that in Dropbox, Google Drive, or whatever your favorite storage medium is, especially if it's a decentralized one. We just worry about what is called a capsule, which is essentially just like an encrypted key way of gaining access. So we don't actually transfer or re-encrypt this bulk. Say if you want to re-encrypt a gigabyte of data, you don't re-encrypt a gigabyte of data. You re-encrypt like a 32-byte private key, encrypted private key, and that's it. So what's going on here is that this terminal at the bottom right is going to be talking to the terminal at the top right. So with that copy there, I need to do. So we're going to be working with Enrico now. Enrico is the data encryptor. So I'm going to run this in the other terminal adjacent. And all I need to run Enrico is the policy encrypting key. And I'll paste that in there. That's what we got from this output of this call here. So we actually just got this policy encrypting pub key. We're using that to run Enrico over here. Go ahead and run that. There we go. Now we get Enrico's verifying key. What Enrico's verifying key is, it's basically just like a public key to a signing key pair. That way you know that some data has actually come from that device itself, right? So before I put this request through, I'll just be going over that. Enrico is running on that port over here, 51 to 51. And we're going to be sending a HTTP request to it. Just at the endpoint of /encrypt_message. And what this is doing is you're just sending some plain text, and it's just going to encrypt it. Normally, you'd be like, oh, I shouldn't send plain text over the wire. You're right. You should not send plain text over the wire. But that's because we're running this on localhost. So it's only safe on a non-shared system. And if you're using a shared system, you probably don't want to use this. Ask yourself what's in your threat model, what are you worried about, what are your attackers are, and what access they might gain. So in that case, don't run stuff on shared systems. And that's just something we're not going to really worry about is security on that quite yet until we actually set up maybe some TLS or even just switch to a different framework like Noise. If you're familiar with Noise Signal, WhatsApp uses it. Anyway, we're going to be encrypting the message, this plain text here, hello, SF cryptocurrency devs. And the request is a base 64 encoded message, just in this dict here. And we're sending that response there, and we get something back called a message kit. What a message kit is basically just everything that you need to re-encrypt it. So you'll get, portion of that will be the actual encrypted bulk data, so that message, hello, SF cryptocurrency devs, which if you're wondering is encrypted with Cha-Cha-20 Poly 1305, which is an AEAD designed by Daniel Bernstein. Some other people may need like AES to be compliant with some framework, but we don't worry about that right now. And then we also get in the message kit is a capsule that is actually what's going to be re-encrypted.
So this is just API calls here to encrypt everything, make the
Yep.
message encrypted,
Pretty simple.
and then post it.
Yeah, it's literally we're just posting a plain text and getting back a ciphertext. So that's all Enrico is doing in that lower left terminal there. He's just encrypting data. So there we go, we got it back. So you can see that bottom left there. He performed the encryption and received it. So now we're going to go ahead and try something a bit weird. What happens if Bob tries to gain access to this data when he hasn't been granted access by Alice, the data owner, yet, right? So say he sees something in a public blockchain or like a public storage medium like IPFS and tries to pull it down and tries to say, I want this decrypted for myself. So what I'm going to do is I'm going to spin up Bob, same flags that I did on the previous terminal. Pass in a teacher URI. So he's also going to go through the learning process. There he is. So we have two keys. This is Bob's verifying key, which is like a signing key for him, or a public key for a signing key, and also his encrypting key, which is the actual key that in our policy is going to be Alice is going to be re-encrypting for that key. So that's the key he'll use to decrypt his data. I need to set this down here. Oh. Don't do that. Oh no, things are going horribly. Live coding is a pain. All right, I'll just do this instead. And then let me set Bob's encrypting pub key. Oh boy, you can see all this error all of our verbose error logging in the event that we get an error. There we go. So let me play this response here. It was a 500. Why was it a 500? Bob didn't actually have access to that data. He just tried to perform a re-encryption, and the network was like, sorry, you don't actually have access to the data. There's never been a policy that exists for you on our network. I can't literally give you access to this data. Even if you were to hack me and try it, I couldn't do it. Alice has not given you access. So what we need to do next is give Bob access. And I'm going to be doing that here. So what we're going to be doing is talking back to Alice, talking to our top right terminal here again. We're going to be calling an endpoint on her called /grant. To do that, we provide a few things. Provide Bob's signing key and Bob's encrypting key, which are those two things that you saw up in the top left terminal there. And then the M and N value. What that is, that's our threshold value. If you remember, we have threshold proxy re-encryption, which means we have to go to a minimum number of nodes on our network to perform that re-encryption. So we need a quorum to pretty much say, I have that re-encryption key, and I can re-encrypt this data for you, of a total of N nodes on the network. So if there are 5 nodes on the network and you only need 3 of them, then you don't need to go to 3 nodes of those 5 and get re-encryption services performed. And then so we also provide the label SFCDEVS so that you can gain access to that data as well, so that the nodes know what the policy is, right?
So the idea is N is the amount of people you're sending it out to, and N is the amount of people you have to talk to get it.
Right, so N is, that's pretty much it. N is like the total number of the nodes on the network that will receive this re-encryption fragment, and M is the number of nodes you have to talk to gain access to that data. So we'll go ahead and make a put request onto that endpoint. Let's hope it works. We got a 200, so that means it worked. On the NuCypher testnet, Bob has now been granted access to this data. All right, so we're going to try what Bob did just previously in the previous step and see if he has access to this data now. So I do the exact same request that I did up there. I make a request to Bob in this daemon running here. And I have the retrieve endpoint, the data that I'm retrieving. And I'll decode the output of this plain text to see if it's actually the plain text we encrypted. It is. Hello, SF cryptocurrency devs. So what happened here is Alice encrypted some data with her own public key and then uploaded that data to somewhere. It doesn't have to be anywhere like IPFS. It can be anywhere through a side channel of your choice. And then Bob goes to the network and says, I want to access this data. She grants access. And then Bob goes back to those nodes and says, give me access to it. They re-encrypt it for him. And now he can decrypt it with his own private key. So the data that was originally encrypted with Alice's public key was re-encrypted for Bob's public key and then decrypted with Bob's private key. And at no point did any of the nodes that we went to on the network actually have access to that plain text. Now there's one thing I have to show you that I'm kind of cheating on right here, is this m and n value is 1. Normally, you shouldn't do this. And you should probably just never do this. The problem why I have to do this right now is we're in the middle of some rapid code movement and trying to get stuff merged. And for whatever reason, the endpoints that I'm using here, something's broken, can't use more than one node for whatever reason. We're figuring it out. It should be fixed soon. And from what I'm told, it's already fixed. But for this demo, I just couldn't get it going. But you should please, when you're working on this yourself, use your whatever threshold you want. I always recommend 3 of 5. It's a good threshold for at least for our testnet. It's small and lets you build really cool applications with it.
So let's say I'm Bob then. What if Bob can't find the 5 people he needs to go perform that re-encryption?
So if your policy has 5 total nodes that have received a re-encryption and you need 3, if Bob can't, if I'm assuming what you're saying is you can't reach that threshold number of nodes, right?
Let's say there's like 10,000 nodes, Bob only knows about half of them, and then only out of half of the nodes, like 2 of them have the data.
Right.
He doesn't have access to the third one.
Yeah. So the question is, what if Bob can't find the nodes that actually has the re-encryption key to perform it? Well, in that case, Bob won't gain access to the data, and that's a problem. The way you can solve that is by either lowering the threshold and also increasing the number of nodes that are receiving this fragment. So if there are, let's say there's 1,000 nodes on the network, chances are, if you're staking a good amount of money to run a node, if you go down, you obviously won't be performing your services, right? We actually have something baked into our smart contracts here that will be, like I said, we'll be deploying the decentralized variant of this soon. And what they will have to do is check in every day to receive their rewards. And if they don't check in for that day, they won't receive re-encryptions or re-encryption fragments, and they won't receive their rewards. So if they don't actually maintain some uptime, they'll not receive anything. But in your case, yeah, you can raise that N number so more nodes on the network get it, so you have more of a likelihood of finding nodes that know about it, and then lower the threshold so that more nodes can actually perform the re-encryption for you as needed.
Okay, is this also fault tolerant? So let's say you have 3 people to have your data, 2 of them go offline. Does the one peer who still has it, does he go and communicate with other people and redistribute it? Or is it just kind of... No,
we don't do that quite yet. Okay. No, well, we need to figure out how to, that's actually an open problem we have on the network. But this is another thing about decentralized applications too, is that a downtime, we call it like this fundamentally reduces to the Oracle problem, right? We don't know when a node is down reliably. What if we can't incentivize nodes to stay up online either, because the moment we do, we're also incentivizing maybe attackers to attack the network, even if they don't get rewards, right?
Wait, if you incentivize people to stay online?
If you incentivize people to stay online, say through like a penalty, right? So if a number of nodes say, hey, the node A is offline, / their stake or something, then that's a problem. Because right now in Dash nodes, that is a problem. You can just pretty much lie to the network and say, so-and-so is offline, right? So we can't do that. We've come up with that. We simply just can't do that. The moment you do that, you're incentivizing other attackers on the network to attack the network and to bring it down. Because then, oh, well, it's really easy to take down the NuCypher network, just have it basically eat itself just by bringing nodes down. So we can't do that until we know somebody is down maliciously, meaning that they just refuse, they're staking, but they refuse to perform re-encryptions, or if they're being under a denial of service attack. And until we can actually determine that, it's a really hard problem to solve for just healthy networks in general. But yeah, that's the NuCypher demo. I hope you guys enjoyed it. Again, docs.nucypher.com, run nodes, build cool shit, and join the CoinList Hackathon. We'd love to see what you're working on. Yeah, thank you.